In this lecture, we're going to continue with the topic on wave transformations. So how do we estimate wave overtopping? Here, wave overtopping usually is estimated in terms of the volume of water, so that we are able to design for the drainage outlet such that any seawater that overtop the coastal structure to the land side can be drained back out to the sea again. Now for monochromatic wave, the overtopping volume given by Q in the equation here can be estimated using this expression. Take note that the Q here takes the unit of meter cube per second per meter. That means it is volume per unit time per unit length of the structure. Now the equation is valid only for this range of the ratio H minus ds over R, whereby H is the crest height measured from the seabed, ds is the toe depth, R is the theoretical run-up height. And if we look at the equation has this bracket here, which is a square root. It has G, it has Q naught asterisk. Q naught asterisk is basically going to be empirically determined together with the value alpha here from the chart on the next slide. And it has this H naught prime, which is the equivalent deep water unreflected wave height. Over here we have exponent, okay, with a negative sign here and the square bracket. Inside here we have R again, H again, and ds again. Take note that in this formulation, when H minus ds is larger than R, then the overtopping volume will be equals to 0. Here essentially what it means is that if the crest height minus the toe depth is larger than run up, then of course no water can overtop to the land side. If H minus ds is larger than R, then Q will be equals to 0. This is example of the plot to determine the overtopping. What we are trying to get from this plot is the alpha value and the Q naught asterisk value given at each of these locations. Alright, and this plot is only valid for a vertical structure like this. We need to know what is the ratio of ds over H naught prime and also H naught prime over gt squared in order to locate the position. And let's say our position is here, then we will get the alpha and the Q naught asterisk value from the nearest points, which are these 4 points. So we may have to interpolate to obtain the alpha value and the Q naught prime value. This is another plot for a different structure type with a slope. And lastly, if we also consider the wind effect on overtopping, then we will multiply the Q value estimated from the earlier equation with K prime, where K prime is given by this equation over here. WF is a coefficient which depends on the wind speed, and the typical value for WF is given here for different wind speed. H, ds, and R are the same definition as before, and theta here refers to the slope of the structure. Last but not least, but we are not going to cover in detail in our lecture here, is to estimate the breaking wave forces. If we have a coastal structure that is located where the wave breaks, then obviously our structure will be subjected to intense or extreme dynamic impact force due to the breaking wave, and long-term exposure to this kind of impact force can actually cause the structure to suffer localized damage. So it is very important then for us to be able to estimate the breaking wave forces so that the structure can be designed accordingly. As we can see from this slide over here, how a breaking wave can be very intense and extreme. And for those of you who have the experience of watching this real wave in action in close proximity, even watching them on video on YouTube, then you obviously understand that the wave breaking force is very important to any coastal design to avoid failure.